Hello everyone, a very warm welcome to all of you. Myself Ashutosh Bajpai, along with my co-authors Aaryan Goyal, Atif Anwer, and Tanmoy Chakraborty from IIT Delhi, presenting our study titled Temporally Consistent Factuality Proving for Large Language Model. Temporal reasoning is an ability in large language models to comprehend and reason for the nuances in time-sensitive queries. In literature, temporal reasoning has been broadly categorized into three different types. The first one is time, where the query and the expected model response both contains the explicit temporal information. In the second type, which is time and event relation, where the query contains the explicit temporal information, but where the model expected response could be an event or an entity. The final type, which is event, is a complex one where both queries and models expected response contain the implicit temporal information often represented by an event or an entity. Now let's look at an example where we have two queries Q1 and Q2 which are paraphrased to each other, which means they carry similar intent but they differ on their surface form. Now let's look at the possibilities of model responses. The first possibility where model respond incorrectly for the first query but model response is correct for the second query Q2. In this case, model behavior is quite inconsistent. The second possibility is where model incorrectly respond for both Q1 and Q2. But in this case, model behavior is quite consistent. The third and final possibility where model respond factually correct for both the queries Q1 and Q2. So the model behavior is also quite consistent, and this is what defines the temporally consistent factual. So before setting up the formal task structure and the associated data set to evaluate LLMs for these traits, let's look at the intuition behind it. So let's hypothesize the model's hyperspace is three dimension where the first and second dimension represented by a subject and a relation, and the third dimension is represented by a temporal axis. So the entities associated with a particular subject and relation uh, can be differ on this temporal axis, and they can be either a forward association or they can carry a forward association or a backward association with another entity. Now, the formal task structure for the novel task, which we call TeCFaP, temporally consistent factuality probe, is as this. So we have a set of base patterns represented by a pair of subject relation, and then we have set of entities E, which is associated with a particular subject relation, and then we have a set of patterns which contains the paraphrases of these of various base patterns in either of these direction backward and forward. So the final set candidate C, which contains the set of tokens, which is a kind of a possible set of vocabulary space for a particular subject relation pair. So next, we construct the TEMP-COFAC, a very comprehensive data set to evaluate temporarily consistent factuality in large language model. It contains the 66 diverse subject relation pairs, which spans around 700 entities, and these 700 entities can be broadly categorized into 11 different types. And the distribution, if we see, it's a kind of natural distribution where the entity names such as person and location are dominant in the data set. The next, we evaluate using this novel data set and the task formulation which we have set up, we evaluate mid-size large language model for their ability in temporally consistent factuality. So we define three metrics to evaluate. The first one tracks the temporal factuality, the second one tracks the temporal consistency, and the final is a kind of third one, which is the unifying metric, which kind of simultaneously tracks the consistency and factuality. And this we carry out in both the direction backward and forward. And then we average it out to get the average performance across both these directions. What we find is the performance of these mid-sized LLMs for this trade is kind of quite unsatisfactory. Uh, and then along with the zero shot, we also carry out experimentations in different settings. The first one we tried out is the in-context setting, where we provide few examples and we see the model performance increases given few examples, but then it's saturated as in the any other case. The second one is we kind of try to find it out that the performance across temporal axis. So what we find, the entities associated with historical time frame, the performance is much better compared to the contemporary, the entities which are or kind of belong to contemporary time period. The third experiment which we do is to compare the open and closed vocabulary setting, and we find that model, when it is restricted to a particular closed set of tokens, then it performs much better compared to the open vocabulary setting. Now, given the destitute performance of LLMs for temporally consistent factuality, we propose a method called consistent time-sensitive learning framework, CoTSeLF, which is a combination of a multitask instruction tuning followed by consistent time-sensitive reinforcement learning to enhance the model's ability for temporally consistent factuality. So the multitask instruction tuning is kind of a very vanilla structure where we have a joint objective of simultaneously fine-tuning the model's parameter theta for both these tasks, consistency and factuality. And then we have two different settings here that one is with context and another is without context. In case of RL component, which has we defined or proposed two different variants of CDSRL. The first one is the discrete variant, where the positive and negative rewards are discrete values, and the final reward is kind of weighted average of the rewards for model to be consistent and to be factual for the same query. The sensitivity parameter alpha is kind of for the which kind of defines the how much weightage we give model to be consistent. The second variant, which is smooth CDSRL, is kind of which solves another challenge where if you see temporal axis is a kind of continuous scale rather than discrete. So if model is kind of factually incorrect, but how far it is from the correct answer, right? So if it is farther away from the correct answer, we have to penalize the model more rather than an answer which is closer or nearby to the correct answer. So we have this smooth variant of CDSRL which solves or which penalizes the model based on the relative distance of the incorrect answer from the correct answer on the temporal axis. Next, we kind of evaluate the CoTSeLF with various strong baseline, and our finding reveals after this thorough examination of CoTSeLF in comparison to very strong baselines that CoTSeLF was able to outperform in enhancing the temporally consistent factuality in large language models across various metrics. Further, we try to find it out if CoTSeLF is able to scale with the underlying models parameter size, and what we found is CoTSeLF is quite robust and it scales with underlying models parameter size. The next set of experiment, we try to find out the association of entity types and temporally consistent factuality. What we find is generic entity types such as person and location names perform destitutely in comparison to specific entity types such as software and satellite names. Thank you for joining us in this presentation.